Okay, and we are finally here. All right, so this is the close this. Yeah. So this is the second round of training for my Oxford presentation, which is going to be happening tomorrow. And there was some changes to the presentation. Not major changes. It preserves the most of what we had before. But now we are going to actually have a few hours of training until we can get this perfect for tomorrow. And yeah, let me just double check if the presentation is... Oh, okay, it is. Yeah. Oh no, the audio is too low. Yeah, it's far too low. Okay, let me do this. And let me increase the gain probably. Okay. Test, sound. How are we doing now? Probably better, right? No, still too low. Okay. Okay, now we should be... Are my headphones still low? No. Yeah. That's much better. Let me increase just a tiny bit more. Okay, there we go. Okay, so we have audio, we have video. We still don't have the media things. We are there, basically. Live, WhatsApp. All right. Let's get this over with as fast as we can. What? Not really. Okay, my mom's traveling. She's in the middle of Amazon, and she's just texting me, so I cannot not answer her. So just a second. Actually, let me switch back to the... Okay, we are back, finally. So, presentation mode, I haven't gone through this fully yet, so this is literally the first time for this new version. And we're probably gonna get it right on the second or third trial. Ugh. Or as soon as I wake up. Okay, so that's it. Just like before, so I'm going to talk about dolphin brains and the shape of brains and why dolphins are different and how are they different. And this presentation is going to be divided into two sections. The first one is going to be a theoretical and context section, and the second one is going to be where we are actually going to dive into the dolphin brains and define their difference and everything. So just to make very clear, I want to talk about the structure or the anatomy of different brains. But I'm a physicist, and the way that I'm going to be doing this is through mathematics. So I want to describe how are all of these shapes connected, and how are we going to describe those shapes, and also to quantify how are they different. Okay, so this first bit is already not that great, huh? Okay, I'm trying this again. So this is going to be divided into two sections. The first one is going to be a theoretical and complex section, and the second one is going to be where I'm actually going to introduce the dolphin brains that I'm trying to describe. So I just want to make very clear that I'm going to be talking about anatomy, morphology, but I'm going to do this under the perspective of a physicist, because what I want to do is to quantify those differences. So I'm going to be talking about a mathematical model that allows us to do this and to group or separate different brains. It's also not great. So, this is interesting how I'm gonna talk about this. So I want to talk about brains. And this has to be very clear. So I'm going to talk about brains, and I'm going to do it in a mathematical way so that we can I'm going to do this in a mathematical way, a quantitative way. Okay, so I'm going to be talking about brains, and why are they? I'm going to be talking about the anatomy of different brains, of different animals, and I'm going to use a mathematical object to describe those brains. Okay, so I'm going to use a mathematical object, and I'm going to use mathematics. Better. So I'm going to use mathematics to numerically describe similarities and difference in the anatomy of brains. And the mathematical object that we are going to use to model all of the brains, all of mammalian brains, is a fractal object. Okay, yeah, this is better. Okay. So this presentation is going to be divided into two sections. The first one is going to be a theoretical section, and the second one is going to be the application of this theory to analyze and describe dolphin brains. So I want to make very clear that I am going to talk about morphology and anatomy of brains, but I'm going to use a mathematical model to do that, and I'm going to describe similarities and differences that happen across different animals, and the mathematical object that is used to describe those shapes. Okay, so divided into two sections. The first one is theoretical, and the second one is going to be an application of this theory to analyze dolphin brains. I just want to make it very clear that different brains. So first things first, I just want to make it very clear that although I'm going to be talking about morphology and anatomy of brains, I'm going to do this using mathematics. And I'm going to be quantifying similarities and differences using a mathematical model or using a physical model. And this physical model is based on a mathematical object called a fractal. And what is a fractal? The fractal is a mathematical object that is generated by a recursive rule. So in the case of a star, what we have is that we get one of its edges, we cut it into smaller pieces to create new corners. And similarly, what we have happening in a mammalian brain, in the mammalian cortex, is something, and okay, talking about mathematics, a theoretical and physical model of the brain. And this theoretical model is based on a mathematical object, and this mathematical object is a fractal. A fractal is just a mathematical object that is generated by a recursive rule. And this recursive rule gets repeated, is a mathematical object that is generated by a recursive rule. So in the case of this star, we have one of its sides get cut into smaller pieces to create new corners and do this over and over again. In the case of the brain, we will have a patch of its, we will have a, we will have a part of its surface area cut into smaller and smaller pieces to create new gyri and sulci. This type of mathematical object it can be expressed in terms of certain y. It's going to be proportional to a certain x to a power r. In the case of the brains, what we have is that the geometrical variables that are involved into defining what fractal object the brain is are the ones as shown on the screen. So we have the total area, the total surface area of the cortex. So we have AT, which is the surface cortex. Holy shit, man! What the fuck is going on? Really? Okay, let's start over. Okay, so this presentation is going to be divided into two sections. The first one is going to be a theoretical section, and the second one is going to be the application of this theory into dolphin brains. So I want to make very clear that I am going to be talking about anatomy and morphology, but I'm going to be doing so in a quantitative way, in a mathematical way. And I want to describe this convoluted shape of gyri and sulci in terms of a mathematical object. And this mathematical object is a fractal object. You might be asking, what is a fractal object? A fractal object is one that is created by a recursive rule in mathematics. So in the case of a star, we can get one of its edges, cut it into smaller pieces to create new corners, and we do this over and over again to create a more complex shape. In the case of a brain, we will have a certain patch of the cortical surface area, and we would cut it in smaller and smaller pieces to create new sulci and new gyri. This usually can be expressed in terms of a certain y. It's going to be proportional to a certain x to a power r. In the case of the brain, we want to express this y and x in terms of the geometrical variables that we see in the anatomy of the brain. So it is possible to show that with this relationship, we are able to express what is the fractal shape of the brain, how it is folding and how it is creating gyri and sulci. So we have the AT, which is the total area of the gray matter surface, times the square root of the average cortical thickness, should be equal to a constant k, times the exposed area, which is the area of just the gyri excluding the sulci, to the power of 1.25. So this geometrical relationship defines how the brain is folding into itself. And it is very interesting to note that all of the terrestrial mammals actually follow the same rule. They have different values of total area, thickness, and exposed area, which they have the total area and thickness, which is defined genetically somehow, and this actually crumples up to form a gerified brane with a certain exposed area. What is interesting to see is that since they all follow the same regression, this means that the same constant k, they all have the same constant k, and we're going to the same constant k, and they also have the same rate of folding, which is 1.25. This constant k seems to be the same to all terrestrial mammals, but there might be an exception group, which is the cetacean group. And so what is this number k? Is it meaningful somehow? And the answer is yes. This parameter k encompasses the biological properties of the tissue that we are analyzing, which is the gray matter, but also the physical properties of the physical constraints of the system. In terrestrial mammals, the physical constraints that generate gerification would be the internal axons on the white matter that pull the brane inwards, but also that the atmospheric pressure that pushes the brane to crumple into itself. And in the case of the cetaceans, if this relationship is valid, they would also have an added hydrostatic pressure since they live underwater, which would make the cetacean branes fold even more. Good. And this is going to be the prediction that we are going to test in section 2. To also test this model, we need to acquire the data for the total area, for the areas and the thickness. And we fortunately have the means to do so. We have, for example, FreeSurfer, which is a tool that allows us to transform from MRI data into surface data. And this is routinely done for humans and some other species. But if FreeSurfer doesn't work, we also have alternative tools such as Stitcher that allows us to transform from manual contours into triangulated surfaces, just like FreeSurfer, and it is generalized to any species that we have manual contours that have been manually segmented. And finally, to finish the first section, we are going to do 2 mathematical enhancements to improve the quality of our data, to better 2 mathematical enhancements to better express both the k parameter and the 1.25 exponents, which are the 2 main aspects that characterize the brane. We are going to do this in 2 steps. First, we're going to make a variable transformation, so from the variable transformation, and the second one is going to be a computational method. Okay. So the first thing is that we are going to transform from the total area, exposed area, and cortical thickness into parameters that I'm calling KSI. Enough. Okay, that I'm calling KSNI. And we are doing, okay, like I said, we are doing this to more promptly extract the values of the k and the exponents. And what would be those k, s, and I? Do they have a easy to interpret k, s, and I? And also we want those k, s, and I variables to express meaningful information that we can easily understand. No, this is not good. This is just not good. I mean, this changed. And which first version? Okay. I'm really not liking this. Not at all. Okay. So let's just start over. Okay, so I'm going to be talking about the shape of brains in general, but more specifically about cetacean brains or dolphin brains, and why would they be different. I want to make it very clear that although I'm going to be talking about different anatomies of different animals, specifically focused on dolphins, I'm going to do this in a mathematical way, and I'm going to express the anatomy or the morphology of those brains in terms of a mathematical object that is based on a physical model. And this mathematical object is called a fractal object. And a fractal object is nothing more than a mathematical object that is generated through a recursive rule. So in the case of the star, we get one of its edges cut into smaller pieces to create new corners and get complexity. In the case of the brain, what would happen is we get one patch of the surface area, we divide into smaller sections and get the sulci and gyri formed from this procedure. This mathematical object can usually be expressed in terms of some y proportional to some x to the power r. And for the brain, what we want is that y and x should be some anatomical feature that we know. It is possible to show that this would be the valid relationship for expressing the fractal properties that are causing the gyrification of the brain. And they are a relationship of the geometrical variables of the surfaces of the brain. So we have the total area, which is the area of the gyri and sulci of the gray matter, times the square root of the average cortical thickness, and this should be equal to a constant k, times the exposed area of the cortical surface, which is the area of the gyri only, excluding the sulci, to the exponents of 1.25. And this fractal relationship that explains how the brain is gaining its gyrification is actually valid for all of the terrestrial mammals. Since they all follow the same regression line, they only vary by AT, T, and consequently AE. No, it's not good. And they all follow the same line, meaning that although genetically they have some definition of what their thickness will be, of what their total area would be, and physically this leads to an exposed area or an amount of gyrification, they all follow the same regression, meaning that they all follow the same k value, they all have the same k value, and they all fold in the same rate with the 1.25 exponents. The only seemingly exception are the cetaceans. And why would cetaceans be different according to this model? It is all related to this k parameter. And this k parameter encompasses the biological properties of the gray matter, which is what is folding, but also it encompasses the physical properties of gray matter. And the physical properties are the forces within the system. So we have the axons that pull the brain inwards inside the white matter, they pull the gray matter. But also they have the atmospheric pressure, for example, which pushes the brain also inwards to make it gain gyrification. In the case of cetaceans, then, they would have not only the atmospheric pressure, which are present in all of the terrestrial mammals, but they would have the added hydrostatic pressure, which would make the brain gyrify even more than the terrestrial mammals. So this is why they have an upward shift in that plot. Good. So this gives us a rough idea of how we're going to test the model. We have cetaceans, and if the model is valid, they should also follow the same exponents of 1.25, but they should have a higher k value. Do we have the tools to test this? And the answer is yes, we have tools that allows us to transform from MRI images into surface images so that we can extract the geometrical variables, the surface areas and the cortical thickness. One of these tools is FreeSurfer, which is routinely used for humans, for example. But also we have alternative tools that applies to all of the mammals, that could be applied to all of the mammals, not only humans, one of which is Stitcher, that allows us to transform from manual contours into triangulated surfaces, just like we get from FreeSurfer. So we have the means to acquire the necessary data. And finally, to finish the first section, I'm going to be talking about a mathematical enhancement that is necessary to better extract the values of k and the exponent of 1.25 to be certain that it does remain the same across different species. And this is a couple of steps. One is going to be a mathematical transformation, and the other one is just a computational method that is just a sophisticated computational method. It is a computational method, period. The mathematical transformation is as follows. We are going to change from total area, exposed area, and cortical thickness into a three new variables that also make sense, and we can also interpret them quite easily. The first one is going to be the k variable from the KSI model, which is related to the forces and pressure of the system. And this is very easy to derive. We just isolated the k from the previous equation and take the logarithm, since we are going to be expressing this, and take the logarithm of k. The next two parameters, I'm not going to derive them, but I'm going to explain them. So the s and I, they are both going to express respectively the shape and complexity or geometrization of the brain, and I is a variable that expresses sizes. It is possible to show that to acquire this information from the AT, AE, and T, this would be the relationship, the mathematical relationship that you would need. And for the rest of the presentation, I'm going to be talking just about K and S, because I'm going to be normalizing different brain sizes, so we can easily compare a chimp to a whale, for example, and we are not taking into account, because it is not interesting to us, the difference in size of those brains. And after the computational method, I'm going to explain how to read a graph of k by s and how to extract those informations from this plot. But firstly, the computational method, which is the last step that we need. So for cetaceans, we usually only have one data for one species, because the material is so rare and hard to acquire that we can't actually have a large sample size. So we have a problem, and we need to solve this by a computational method that allows us to increase the amount of data that we get per subject. And this method does that. So if we have a surface reconstruction of the final actual surface of the brain, what we can do is to transform it back into an image. Then we lower the resolution of the image, and we transform it into a lowered resolution surface. And we do this procedure recursively until we reach a final form, which is the base shape of this brain. And this procedure is basically doing the inverse model of what I showed at the beginning with the star. So instead of adding new cortical features, instead of adding new gyri and sulci, we are instead removing. But what this does is basically it allows us to transform one brain from one single subject into a collection or series of points that will then allows us to extract the total, the k parameter and the exponent for one single subject, instead of having the regression of multiple species with multiple subjects in that plot. And that's not good. This is really not good. Okay, so how I'm gonna do this. First things first, this is way too long, right? Need to put a clock. Random clock. Okay, let me try this again. Okay, so I'm gonna be talking about brains and how dolphin brains are shaped differently. And this presentation is going to be divided into two sections, the first one being a theoretical and context section, and the second one being the actual application of this theory to analyze dolphin brains. And I just want to make it very clear that although I'm going to be talking about morphology and anatomy, I'm going to be doing such in a mathematical way. And I'm going to be using a physical model that explains how the brain gains its purification and where it is coming from. And it is based on, I'm going to be using okay, so I'm gonna be talking about dolphin brains and how they shape differently, but I'm going to be doing that in and this presentation is going to be divided into two sections. The first one is going to be a theoretical section, and the second one is going to be the application of this theory to analyze dolphin brains. So basically, what I'm going to be doing is that I'm going to be using a theoretical physics model to express the anatomy and the morphology of the different brains, and I'm going to be using mathematics to do so. So I am going to be talking about anatomy, but I'm going to do this in a mathematical way. And the mathematical way that allows us to compare different animals is to talk about fractals. And fractals are mathematical objects that are very interesting. And I cannot present it, okay. That are very interesting, and they are conceptually very easy to understand. So these objects are generated by a recursive rule. In the case of this star, for example, we have one of its edges that is cut into smaller pieces, and then we create new corners and add more complexity to the shape. And we do this over and over again until we finally reach the final form of this shape. In the case of the brains, we would get one patch of its area of the cortical surface, and we would cut it into smaller pieces. And from this step, from this procedure, we would gain sulci and gyri, which are the cause of the gyrification. This usually can be expressed in terms of some y that is meaningful to us. Is going to be proportional to some x to a power or exponent r, which characterizes the rate of gaining this gyrification of the objects that we are analyzing. It is possible to show that in the case of brains, of real brains, this is the mathematical relationship that explains the rate and the cause to why the brain is gaining its gyrification. And what we see is that this is a relationship between geometrical variables of the surface of the brain. We have the total area, the AT, which is the area of the sulci and gyri of the gray matter, times the square root of the average cortical thickness. And this should be equal to a constant k, we're going to talk about it later, times the exposed area, which is the area of the gyri only, excluding the sulci, to the power of 1.25. And I'm not going to derive this, I'm just going to show a plot to see how well does this model fit into the data that we have. So this is the regression that we have for all of the terrestrial mammals and also the cetaceans. What we can see is that although different animals define genetically probably their values of total area and their values of cortical thickness, which leads to a different exposed area, to a different purification of how compact the surface is, how crumpled it is, they all follow the same regression. And if they follow the same regression, this means that they have the same constant value. So this is a universal for terrestrial mammals, and they have the same gaining rate or the same exponent, which is the 1.25, which means that this law of purifications is seemingly universal. The only exception, it seems, are the cetaceans. And why would this even be the case? Well, it is all related to this number k. So this number k is not a random number that we just adjust. It actually encompasses all of the biological properties of the gray matter tissue, but also the physical properties of the gray matter. And the physical properties are the forces which are involved into the system. And you might be thinking, what forces? Well, the gray matter lives on top of the white matter, and the axons inside the white matter are pulling the gray matter inwards. Additionally, since we all live under atmospheric pressure, the atmospheric pressure also crumples the brain inwards, so it makes gain more purification. So cetaceans are special creatures that live underwater, and so not only they are submitted to the atmospheric pressure, but they also live under a high hydrostatic pressure due to the water. So this should make them have a higher K value, would make them shift upwards on that regression line. And this is why they should be an exception. Great. So how can we test this? Well, we can use a variety of computational tools to transform our data from MRI data into surface data that we can then plot into the model. So for example, we have FreeSurfer that does that routinely for humans and some other primates. But also, if FreeSurfer doesn't work for whatever reason, we have tools such as Stitcher, which is a tool that I developed during my master's, that allows us to transform manual segmentations into triangulated surfaces, just like FreeSurfer does. And so we have the means to actually test this model for any species that we want. Good. Just before we go into testing the model, I want to make two steps, which I'm calling the enhancement steps, that allows us to better explore the model. The two steps are a mathematical transformation, so it's just a shuffling of those parameters, and yet a new computational step that allows us to gain data for a single subject. So instead of analyzing one brain for one specimen, we are going to have one specimen transform into a series of data that we can then just regress just that single individual and extract the K and the exponents at the same time for one single subject. Okay, what are these mathematical and computational steps? The first, the mathematical one, is going to be a transformation. So from the AT, AE, and T, we are going to shuffle them around and re-express the terms, and I'm calling those terms the K, S, and I. And they are very easy to interpret in what they are. So the first one is going to be K, and K is actually just the same parameter that we saw before. So we just isolate the K, but instead of using the small k, we are going to take the logarithm of K, and this is the parameter that should be expressing the amount of forces or pressures and the shift that we are going to have predicted for the cetaceans. The S and I, I'm not going to derive them as easily, but they are two other parameters that we as scientists would be interested in when analyzing brains. So they are going to be the complexity or the amount of purification that a brain has, and we have one parameter that expresses this entirely. And we have yet another parameter that expresses only the size of the brain. So if you just upscale or downscale one single brain, this should be irrelevant for our analysis. And so we have one parameter that allows us to normalize different sizes of different brains so that we can analyze just the amount of force, and the complexity or the gerification of the brain. This, for math enthusiasts, this would be the actual relationship for all of these three parameters. As you can see, they are nothing more than a combination of what we had previously. They are just rearranged so that we can better extract the information that we want. I'm going to talk about how to read a K by S plot, and for the rest of the presentation, I'm not going to be talking about I. Everything is going to be normalized so we can compare rats and elephants with much more easily. Okay, the computational steps that allows us to magically, and I'm using quotes, magically increase the amount of data that we have. It is very, very easy to understand. What we want to do is basically do the inverse movie that I showed from the start so that we can get to the basic shape of the brain before it got its gerification. So the way we do this, we get one surface from FreeSurfer or Stitcher or whatever. We go from the surface to an image again. We lower the resolution of the image. So we lose details and we lose sort of gerification in this process. And then we reconstruct the surface again from this lowered resolution, lower quality image. We do this it is not an arbitrary way of doing this, but we do this recursively until we reach a final form, which is the basic shape that should be the base shape that generated the original brain that we're analyzing. Okay, and this can be applied to any object, but then if this can be applied to any object or any reconstruction mesh that you have, then how do you read this and how does this apply specifically for brains? Well, this is the movie that illustrates this procedure. So you can see that we go from a base shape or for a final shape into a basic shape, and we do this progressively at different resolutions. And finally, how do we read these plots and how do we interpret this procedure, which is complex and weird, but how do we read these plots? So for one brain, what we expect is that in this K by S plot, applying this algorithm from the right to the left, what we have is the actual complex and final surface brain being melted down. So it loses resolution, it melts. And as it lowers its quality, what we see is a constant trend or a constant line. And this should be true to any of the brains that we have. If they have the same 1.25 exponents, they all should be parallel lines to this one, the constant line. And different heights of this regression actually express different values of k. So we immediately have one way of quantifying the 1.25 exponents, but also at different heights we have one way of expressing the k parameter. So we can extract both informations at once. What happens if a line doesn't follow this trend? So for example, if we have some object like a perfect sphere, well, okay, I need to stop. This is already over 10 minutes. This is bad. Okay, over. Okay, so this presentation is going to be divided into two sections. The first one is the theoretical section, and the second one is the application of the theory to analyze why dolphin brains should be shaped differently. Okay, I want to make it very clear that although I'm going to be talking about anatomy and morphology, I'm going to be doing in such a way that is going to be a mathematical way. And it is going to be based on a theoretical physics model. So without further ado, what is the shape of the brain that I want to express? The shape of the brain should be a fractal object. And a fractal object is simply an object that is generated by a recursively or repeating rule. In the case of this star, we have one of its edges that is cut into smaller pieces to create new corners and new complexity. For the brains, what we would have is that the surface of the brain would have one of its patches cut into smaller patches to create new sulci and new gyri. And this would be the explanation to why the brains are gyrified. These fractal objects can usually be expressed as some sort of y being proportional to some sort of x to a characteristic r exponent that is characteristics of that fractal object. For the brain, what we have is that this relationship is expressed in terms of the geometrical variables of the surface area of the brain. So we have the total area, which is the area of the gyri and the sulci of the gray matter, times the square root of the average cortical thickness being equal to a constant k, times the exposed area, which is the area of the gyri only, excluding the sulci, to the characteristic exponent of 1.25. And so this expresses the rate of gaining of gyrification of the brains, and this should be how we characterize what a brain is. This model is valid not only for humans, but also for all of the terrestrial mammals that we have tested so far. And although different animals will genetically probably set their values of the total area and the cortical thickness, the way that it is combined to generate one cramped model with one reduced exposed surface area is seemingly universal. And that is because as we plot this, they all follow the same trend line. So they all regress to the same k parameter and the same 1.25 exponent. The only seemingly exception are the cetaceans, which seem to be shifted upwards systematically. And the reason for this is related to the k parameter. So it is not just a number. This k parameter is the one parameter that should encompass all of the biological features of the gray matter, but also the physical features of what is going on into the system. And these physical features are the forces of the system. In the case of terrestrial mammals, we have the white matter with the axons pulling the gray matter inward, but also the atmospheric pressure pushing from the outside to create more gyrification. And now we see why the cetaceans are, or should be, an exception. They should, since they live underwater, they should not only have the white matter pulling in, the atmospheric pressure pushing, but also the hydrostatic pushing. And so they should have a higher K value, and this is why they should have a positive shift on that plot that distinguishes them from other mammals. And this is what we want to test. To test this, we need surfaces. And tools such as FreeSurfer allows us to transform from MRI images to surfaces, to 3D surfaces. And it usually does that for humans and some other species. In case FreeSurfer doesn't work, we also have alternative tools such as Stitcher that allows us to transform from manual segmentation, from those manual drawn lines, into 3D surfaces that are equally comparable to the ones that we get from FreeSurfer. Lastly, what I want to talk about to finish the first section is a type of enhancement. And what enhancement you might be asking? First things first is we don't have that many data for cetaceans. So we need a way to make them more significant. And we are going to see a computational way of doing this to increase the sample size of one single subject. We're going to transform one data point from one subject into a collection of points that we can actually interpret and read, and that we can use to extract the k values and the exponent values. And we are also going to be talking about a mathematical transformation, which is necessary to better express and to better read the graphs that we're going to see, so that we can more easily and promptly understand if they have the same 1.25 exponents and if they indeed have a higher k value. So the mathematical transformation is going from ATA and T to a KSI, which are all just a combination of those other parameters. But they allows us to better express a few features that we are interested in. So we have the k parameter, which is going to be an isolation of this force or pressure parameter that we are interested in the case of cetaceans. It is fairly easy to derive this one, so this is the one that I'm going to be showing here. You just isolate k from the equation that we had previously, and you take the logarithm of k. The other two I'm not going to derive, but they are going to be expressing the shape or complexity or gyrification of the brane. And the other one is going to be expressing only the size, the total size of the brane. And this allows us to rescale different branes, so we can compare rats with elephants, for example, because we can just normalize all of the brane sizes. And this is what I'm going to be doing for the rest of the presentation. So I'm not going to be talking about I anymore. I'm just going to be talking about K and S, and they are all normalized. For math enthusiasts, this is the mathematical relationship, and as we can see, they are just a combination of the previous parameters that we have. They are not adding anything more. They are just rearranging so that we can read a K by S plot, and I'm going to show you how to read this plot to extract promptly the 1.25 exponents and what is the K value that we are looking for. Before we dive into the K by S plot, the computational tool, the computational procedure that we're going to use to increase the data points for single subjects. It is simply, we are going to reverse the movie that we saw before for the star. We're going to grab one of the surfaces, we are going to transform it back into an image, we're going to lower the resolution in a very specific way, and from this lower resolution image, we are going to transform it again into a surface. And we do this over and over again until we reach a limit. And what is this limit? Essentially, this is the basic shape that was being gyrified, or that was being cut to gain the gyrification, the sulci and the gyroid. So this procedure allows us to revert the movie that generated the final shape, the final gyrified shape of objects in general. Here's a movie that shows this in practice, what is going on. We have one final surface, and it progressively gets less and less complex, and it moves it back into its basic shape. Okay, so how do we read this and how do we interpret this? This will be a K by S plot. For branes, it is very easy, because in this space, K by S, every single brane should have a constant line. And from the right to the left, what we have is a more complex brane, so higher value of S, more gyrified brane. And as the movie goes on, removing the features, we are actually moving backwards in S. So we have this constant line. Different heights, so different heights of this line represent different K values. And so what we expect is that the dolphins are going to be somehow upward with a constant line around here. What about other objects? Well, if we have, for example, a cube that is a lissencephalic from the beginning. If it is lissencephalic from the beginning, it is not girified as a brain, and it has an exponent of 1, let's say. So in this space, lissencephalic or surfaces that are not girified, just like brains, they are going to have different inclinations. And lower inclinations means less girification, with the limit being this black line, which is the totally lissencephalic object. If we have a nut, for example, it is more complex than a cube, but it is not as complex as a cortical or as a cortex. So it is somewhere in between. And if we do this to a bell pepper, it is also less girified than a brain, but it is not as, and this is why it has a different inclination. Okay, so far what we've seen is that we have a theoretical model that we can understand and we can test. We have the data that we are going to use to test the model, and we have mathematical and computational tools, the brain melting algorithm, that allows us to better analyze the model. Good. So the second section is going to be very simple because we already have the base that we need to answer these two questions. So firstly, are dolphins' Ks actually higher, or are we wrong about this? And secondly, how robust is all of those procedures that we are implementing, and how certain can we be of the results that we get from the first question? So to answer the first question, firstly I need to talk about the Brazilian Neurobiodiversity Network, which is a network of different institutes across Brazil in different states that allows us to collect, preserve, and analyze brains of different animals in Brazil. And it is from this network that I got 2 images and 2 surfaces that I'm going to be showing for our analysis of cetaceans. Additionally, this network also allows us international collaborations, which provided me the image of a stellar sea lion. And we are also adding any other resource that we found online for primates, humans, and other species, so that we can compare cetaceans with other animals. Okay, so first things first, us humans. What we are used to analyze and study. So when looking at humans, what we see is that we all follow that same constant line, roughly the same constant line. And we do have a certain span of values, which is this blue band that we see, but it's roughly constant and it doesn't vary that much across different subjects of humans. Additionally, if we use different reconstruction methods, we don't seem to have that much of a difference regarding the results that we get. So both reconstruction methods are fairly good or good enough to represent the cortical shape. Okay, let's add other animals, but not cetaceans yet. Where do they fall on this K by S plot? If we add other animals, so here we have a rhesus macaque, a marmoset, and the stellar sea lion, they all seem to follow within the expected range of K values, and they all seem to also have the same constant line. I mean, they all indeed have the 1.25 exponent, and this is compatible with the results that we've seen previously. So far, nothing new. But then, what about the cetaceans finally? Well, the cetaceans are different. The cetaceans are very different. Firstly, all of the points in the regression are above the expected values for humans and other terrestrial mammals. So this is what we were expecting, a higher K value, meaning that they live in a higher pressure ambient, which drives this higher K value. However, from this regression, we also see that the cetaceans do not have a constant line. So this means that they are not following the 1.25 exponent. It is possible to calculate the exponent for cetaceans, and from our calculations, this exponent falls from 1.28 to 1.30, from 1.28 to 1.3. So what we see here is that cetaceans, although they do seem to have a higher K value, they also seem to have a higher exponent. And this is news. This is very news. Because if they have a higher exponent, this means that they have an added feature on the cortical development, during the cortical development, that allows cetaceans to gain more gerification than would be expected for other mammals, which is a mechanism that we do not see in other species. But not only that, it is a mechanism that we did not predict, and we still don't know how to explain. So why and how cetaceans gain more gerification than other animals is something that is entirely new to us. And we are still investigating why this could be the reason, if we neglected some term during the construction of the theoretical model, that maybe it is present in other animals, but it's just not as relevant as in cetaceans, or maybe it is in fact a new term or a new feature that are exclusive to cetaceans, and we must figure out what it is. Finally, to finish the presentation, what can we talk about how robust this method is? So we are going to do this by introduce errors that we know what they are, and we know how this, or we know what caused those errors, or bad image acquisition that doesn't allow us to segment the brain properly into white matter and gray matter, or doesn't allow us to see fully certain regions of the brain. So this is one artifact that could have happened to cetaceans, and maybe this is what causing the discrepancy. Or in the case of bad surface reconstruction, so if we tend to vary the cortical thickness, which is one bad reconstruction that you could get, how does this affect the reconstruction? So varying the cortical thickness by getting partial cortical thickness, how much does this affect the result that we have? And is this going to be the same result that we see in cetaceans? So are these the reasons why cetaceans are different, instead of they have an actual different cortical gerification mechanism? Okay, so first about the bad images or bad acquisitions or bad segmentations. If we get a database for humans that has good images and bad images, and we don't fix the bad images in any way, and we just make FreeSurfer perform its standard pipeline, what do we get? Well, we see that for humans with good quality images, they have roughly this constant trend of K, and they have seemingly a higher value of K. For bad images, what we see is that there is a trend on lowering the K value, but somewhat preserving the 1.25 exponent. So this is the opposite of what we see with cetaceans. If they had a bad image quality, what we would expect is that they would have a lower than expected K and not a higher than expected K. Okay, and what about the bad reconstructions or varying cortical thicknesses? What we see is that by varying from no cortical thickness at all to the actual cortical thickness, we see also a trend to lower the K value, but also the added lowering of the fractal exponents. So instead of increasing the fractal exponent, which is what we see with cetaceans, bad reconstructions would lead to lowering the exponents. And like I said, this is the opposite that happens with cetaceans. So far, everything that we tested leads to the same conclusion, that if it is a methodological error, so everything that we tested of methodological errors that could possibly explain why cetaceans are showing as different animals in that regression is actually not that meaningful. It's actually the opposite of we see with cetaceans, and this is why we believe that dolphins have their own purification law. And okay, so the takeaways from all of these results are that dolphins do seem to have their own purification law, because everything that we tested showed us that any errors on the pipeline would tend to have the opposite effects on what we see with dolphins. And also that the KSI plot by cortical plus cortical melting is a robust way of describing the anatomy and investigating new is a robust way of investigating brain anatomy in general and getting new exciting possibilities from blah, blah, blah. Okay, so again, okay, did a pause. Okay, let's go back. Okay, real soon. Let me just grab some water. And we are back. Kiddos. Where is... Okay. If I could add sounds. Oh, come on. Oh boy. Hmm. Back to the presentation, huh? Okay. Here we go again. Okay, so I'm a member of I'm a PhD candidate. No, this is gonna be okay. So hello everyone. I'm gonna be talking about dolphin brains or brains in general. So I'm gonna be talking about oh boy, already that bad, huh? So hello, we're gonna be talking about brains and how are they shaped, and more specifically, how are dolphins' brains any different from other brains that we have? So this presentation is going to be divided into two sections. The first one being the theoretical and context section, and the second one being the more applied to dolphins part of the presentation. So I am going to be talking about neuroanatomy and neuroanatomy of different animals, but I'm going to be doing that in a mathematical and physicist way of things. So we have a theoretical physics model that explains how the brain gains its purification, and it is based on a mathematical object that is called a fractal. And the fractal is an interesting mathematical object because it can be defined very easily as a shape that is generated by a repeating rule. So in the case of the star, for example, we have one of its edges that is cut into smaller pieces and creating new corners, and we do this over and over again until we reach a certain limit. Well, for the surface of the brain, you're going to have a patch of cortical area that is going to be divided into smaller and smaller sections, and this allows us to gain the sulci and the gyri. This is usually expressed in terms of a power law in mathematics. So it's going to be a certain y that has a meaning to it, times the proportional to a certain x to a power of r, where r is the characteristic exponent of this fractal, or this rate of gaining complexity for that mathematical object. So for the brain, what we see is that there is a fractal expression that allows us to describe the anatomy of the brain, and it is this one. And it is a relationship between a series of geometrical properties of the surface of the brain. So we have the total area, AT, which is the area of the average cortical, the area of the gray matter with the sulci and the gyri, times the square root of t, which is the average cortical thickness, and that is equal to a certain constant k, times the exposed area, which is the area of the gyri only, excluding the sulci. to the exponent of 1.25. And this relationship is valid not only for humans, but in fact to all of the terrestrial mammals that we could test. And although different animals will have genetically defined values for the thickness and the total area, they all crumple and gain the purification in the same process. So they will have a certain value of the exposed area due to this process. And since they all follow the same regression, this means that they all have the same k value, which is a number, and the same exponent, which is 1.25. The only seemingly exception are cetaceans. And the reason for cetaceans being an exception is related to the k value. So the k value is not just a number, but it is a number that encompasses the biological properties of the material that we're studying, in this case, the gray matter, and the physical properties, the physical constraints of the model that we are studying. So we have internal forces, in the case of the brain, which are the axons on the white matter pulling the gray matter inward, but we also have the atmospheric pressure, which is a force that crumples the brain inward. And since cetaceans do live underwater, this means that not only they are living under the atmospheric pressure of all terrestrial mammals, but they have the added hydrostatic pressure that they are the only ones that are submitted to it. They're the only family, they're the only group that are submitted to it. So this is why they should have a different k value, in this case a higher k value, and a higher an upshift of the regression line. Okay, so can we test this? Well, we can, because we have the tools to do that. We have tools such as FreeSurfer that allows us to transform from MRI to surfaces. This is in the case of humans and some other animals. But for other animals that FreeSurfer cannot be applied, we have alternative tools such as Stitcher, which allows us to transform from manual contours into triangulated shapes that are equivalent to the ones that we get from FreeSurfer. So we can acquire the data and just test the model. But before doing that, before testing the model and see if our prediction is correct, we are going to do a couple of steps. We are going to do a couple of enhancements to our analysis. One of them being a change of variables. So we are going to combine those parameters that we see before in a very specific way, so we can promptly calculate the k value and the fractal dimension. And also we are going to increase the data that we have, literally increase the data points that we have for a single subject. And we are going to do this with a computational method. And this is necessary because with cetaceans, we usually only get one subject per species. And this is certainly the case that we have here. So we could not regress one line per species because we wouldn't have enough data to do that. So how do we do this? Okay. So first, the change of variables. So we're going from the variables that we've seen before to the KSI system. The KSI is very easy to interpret as well. They're not just a mathematical complex way of getting this. They are fairly easy to comprehend. So the K is just going to be related to the forces and the pressures that we want to measure. So we get this number for the K, then we are going to be able to infer what is the total pressure of the system. And it is very easy to calculate this. We just isolate the small k that we saw before from the equation, and we take the logarithm of it. And we can just very easily understand why this is related to k and why this is related to pressure. The next two variables, I'm not going to derive them, but I'm going to explain them. So we are going to have the S variable, which is the shape variable or the complexity or the gyrification of the brain. So how much gyrified it is. And we are going to have the I parameter, which is just the size and not the gerification at all. So we're going to use I to normalize every single entry that we have on our analysis so that we can compare rats with elephants, disregarding the obvious difference in size that they have. And we're going to just analyze the shape, the complexity, and its relationship with the force of the pressure. I'm going to describe how to read one plot of K by S properly, but I'm going to do this after we talk about the computational method. So I said that, oh, and this, for the math enthusiasts, this would be the actual relationship that you need to express those variables that I was talking about. The computational method is, like I said, the way of increasing the data points that we have per subject. And the whole idea is that we want to reverse the movie that we saw for the star. Instead of gaining new coordinates, we want to go from one final form into its basic shape. And we do this by getting the final surface, and we transform it back into an image. And from an image, we lower the resolution in a very specific way. This is not arbitrary. So we lower the resolution and we perform the reconstruction again. And by doing this, we can actually just, doing this over and over again, we can actually reach its final basic shape. So we are going to get a series of points that allows us to regress one line for one single subject because of this procedure. Okay, so finally, if we do this computational method for one brain and we plot it into a, no, before that, this is an example of how this algorithm works. So you can see that we have a final brain shape that is melting, and this is where we are getting the name from, the melting algorithm that allows us to melt the complexity of the brain and get its basic shape. So how do we read this on the K by S plot? If we do this melting algorithm and apply it to a cortex, what we expect to see is, if we have 1.25 for the exponents and only 1.25, in this K by S plot, due to the relationship and how we construct those variables, this is going to mean a constant line in this plot. So from the right to the left, we have a more complex and the final shape, and as we melt down the brain, we're going to less and less gerification until we find it reach its final basic shape. If we get an object that is not a brain, if we get, for instance, the most lissencephalic possible, so a sphere with a certain thickness or a cube with a certain thickness, if we apply the same algorithm, what do we get? We get this line, and this is the line of pure lissencephalic melting. So this is a line that has a different inclination, so the exponent would be not 1.25 in the case of this cube or a sphere or a very basic shape. This exponent would be 1, and this is how it's going to look like in this K by S plot. What if we have other in-between shapes? So you can analyze a chestnut or a bell pepper. Well, they are not totally flat or lissencephalic. They have some complex to it, but they are not as complex as the brain. So we get different inclinations, which are not exactly 1, but are not 1.25. There are something in between. And this is what their regression would look like, or the melting would look like. Okay, so far we have a theoretical model. We have the data to test the model, but more than that, we have some mathematical and computational tools that allows us to better analyze the data and better test the model. And so what we're going to do next is go into the section 2 and try to answer those two questions. So with all that we've seen and with all that we have for computational methods, are dolphins' K value actually higher? So if we do this, what are we going to see? Is our prediction correct or not? Secondly, how robust is this procedure? So can we trust this, what we're doing? And what happens if anything goes wrong? How certain can we be of the results that we're getting? Okay, so for the first question, I need to talk about the Brazilian Neurobiodiversity Network. This is a network of different institutes across different states in Brazil that allows us to collect, extract, preserve, and analyze different animals living in South America. This is the network that allowed me to get 2 images of very high quality 7 Tesla MRIs for 2 cetaceans, and this is also where I'm getting the surface reconstructions from. Also from the network, we have international collaborations, which allow me to get 1 stellar sea lion, which is the one in the middle, and we are going to add every single source of available data that we can find online for different primates or different animals in general, including humans. Okay, so finally, we apply the brain melting to every single one of this. We get a lot of data points. We're gonna get a lot of regressions. What do they look like? Starting with humans, which are the ones that we are most used to. We have an average trajectory that is roughly constant for humans. So this is what we have seen before with the previous analysis, the initial plot. And this means that they do have a 1.25 exponent because they have a constant line. And they have a certain span of possible k values, which means that they are all living roughly with same under the same pressure, and they all live with the same k parameter. Also, what we have here is 1 human subject reconstructed with different reconstruction methods. And we can see that regardless of the method that we're going to use for surface reconstruction, they all tend to follow the same trajectory. They all tend to have the same k value and the same 1.25. So reconstruction methods should not be an issue here. Good. Next, we are going to add other animals, not cetaceans yet. But what other animals, terrestrial animals, should look like in this plot? Again, constant lines with the same k value, because they all live under atmospheric pressure. And this is what we see. So we have rhesus macaque, we have the stellar sea lion, we have marmoset. They all follow within the expected range for the k value, but they don't follow, and they also have a same constant value. So this means that they all have the same 1.25 exponent. Finally, the cetaceans. Well, the stars of the show, they are different. They are indeed different, and they are different by having a higher k value, which is the thing that we did predict before. So this means that they should be living under higher pressure, and this should be why they have a higher k value. However, they do not seem to have that constant of a line. So somehow, cetaceans have a higher inclination. They have a higher than 1.25, and we estimate that their exponent is around 1.28 to 1.3, which means that somehow they are gaining more purification than would be expected from our model. And what does this mean is that they probably have some biological method of gaining more purification than the other animals. They have the means to get more folds than would be normally acquired for a brain of their total area and thickness. And we still don't know what is causing this. Well, for instance, it could be that only cetaceans have this property, this biological property of gaining more purification, but also this could mean that we have neglected a certain term on our derivation of the model that is not going to be that much relevant for terrestrial mammals for whatever reason, but it is relevant when we analyze cetaceans. So it might be that we are missing a term that is present in all mammals, or that cetaceans have an exclusive terms that only they have, and this puts them, this separates them from every other family or every other group of mammals that we have. Okay, so this is exciting, this is new. We still don't know what it is, we still don't know what causes it. We need to investigate why this is the reason. But before this, how certain are we that this is in fact something that they are gaining? This is not a methodological error or anything like this. So how robust is our analysis? Well, what we see here is what we can do to test this is simply just input controlled bad data into our brain melting pipeline and see what happens. So if we have bad quality images, if we have bad quality segmentations, and we feed it into FreeSurfer, what happens in this case? Is it going to be the same that we see with cetaceans? So this is what's going on with cetaceans. It was a bad acquisition or bad segmentation. Or if we instead trick FreeSurfer to create varying thicknesses on the cortical surface, if we just manipulate FreeSurfer to do this and we get a bad reconstruction from this, what kind of results do we get? Is it also what we see with cetaceans? So it was a reconstruction issue and not a acquisition issue. Well, let's see. With bad images, what we have is that the red points have a tendency of having a lower k value, although preserving the same 1.25 exponent, so they have a lower constant k value in comparison to images with good quality and good segmentation. And this is opposite of what we see with cetaceans. Cetaceans have a higher than expected k value, so we are going to discard this as a possibility. Secondly, if we manipulate the surface, so if we create varying thicknesses, what do we get? Well, we get a lower than expected k value, but also we get a lower than expected fractal dimension depending on how thinner this brain actually is. And this is twice the opposite of what is happening with the cetaceans. So if something is going wrong with the cetacean analysis, it is not what we are it is not any of those problems that we are simulating here. And this just and this is the reason why we believe that both the cetaceans that we have are actually in fact special in the sense that they have their own gerification law and not that it was a methodological error. Finally, the two takeaways for this presentation is that dolphins do seem to have their own gerification law, although we still don't know what is causing it. And the second one is that the KSI and brain melting algorithm are a robust way to analyze anatomy of different brains and trying to quantify what is going on with brains, what might be going on when we have bad reconstructions or bad image qualities or stuff like this. And it is a promising tool in general. This is the team that is involved with the research. There is myself, my two supervisors, Bruno and Camila, and also Nina and Luana, which are the biologists and anatomists that perform a lot of the segmentations that we have seen today. And that's it. Holy shit. Okay, again. Okay. Can still do better than this. Oh boy. Okay. Station Pro. Oh boy. I need to be right back. Okay. Okay. That's it. I need to add the medias. Oh, come on. X. Thanks. Okay. That's. And then I need to add the. And the. No. Media and stuff here. Yes. Oh. Okay. Oh, this is weird. This is totally the wrong. Oh, it's totally the wrong thing. Damn it. Okay, never mind. But okay. Okay, let's do one more, right? All right. So Hi, and today I'm going to be talking about the shape of the brain, more specifically dolphins' brains, and why would they be different. So I want to make it very clear that although we're going to be talking about brain morphology and anatomy, I'm going to be doing that in a mathematical way. And I'm going to use a theoretical physics model that is based on a mathematical object called a fractal to do so. And how similar and how different those objects are is what we are interested in. So a fractal object. Fractal object is an object that is generated by a repeating rule. So in the case of this star, what we have is that we have one of its edges cut into smaller pieces to create new corners, and we do this repeating until we reach a certain limit. In the case of brains, what we would have is a patch of a brain surface or cortex that is going to be divided into smaller and smaller portions to create sulci and gyri, the gyrification that we see on the brains. This usually can be expressed in terms of a certain y proportional to a certain x with a characteristic exponent r that dictates the rate of gaining of a certain feature, and this rate is what is going to characterize the cortex in our case. So we have this combination of geometrical parameters that are present on the brain, and they are related in this way, and I'm not going to derive this, but they are related in this way to describe the fractal or the type of gaining of gyrification that happens inside the brain, or on the surface of the brain, should I say. So we have the 18, the total area, which is the area of the sulci and the gyri, the average cortical thickness T, and the exposed area AE, which is the area of the gyri only, excluding the sulci. And they are related in this way with a K parameter multiplication and the 1.25 exponent. Okay, and this relationship is valid not only for is valid for all of the terrestrial mammals that we have tested so far. And although different animals will have genetically defined their values of total area and thickness, they are all bounded by this relationship, which means that they will have a final limit of the exposed area determining how gyrified they are going to be by this relationship. And since they all follow in the same regression line, this also means that they all have the same K value and the same 1.25 exponents. The only seemingly exception are the cetaceans, which seem to be a little bit higher above this regression line. And the reason for this is related to the K, which is a number for sure, but it is not an arbitrary number. It is a number that encompasses all of the biological properties of the material that we are studying, in this case the gray matter, and also the physical properties of the system. So in the case of the brains, we have the axons pulling with a certain force on the inside through the white matter, and they are pulling on the gray matter, which causes the gyrification. But also we have the atmospheric pressure in the case of the terrestrial mammals that pushes the brain inwards, and this would also add an extra force to cause more gyrification. And well, if the total pressure is relevant, this means that cetaceans, since they live underwater, will have an added hydrostatic pressure pushing the brain inwards, making them gain more gyrification as well. So this is the reason why cetaceans should have a higher than expected K value on that regression. To test this model and to see if our prediction is correct, we are going to use a series of tools to acquire surface reconstruction. So we have, for instance, the FreeSurfer, which is a tool that allows us to transform, for certain species, an MRI image into a triangulated mesh. And if FreeSurfer doesn't work, we have alternative tools such as Stitcher that allows us to transform from manual segmentation from these manual contours into also triangulated shapes that are equivalent to the surface that we get from FreeSurfer. So we have the means to acquire the data to test our model. Finally, to finish the first section, I'm going to talk about a certain mathematical and computational enhancement that we need to firstly increase the data points that we have, because with cetaceans, since they are rare specimens, we don't have a collection of cetaceans. We don't have that many citations to make a regression to derive the exponent and the k value properly. So we need a way to increase the sample size, and we're doing this computationally. Also, instead of plotting that initial plot that I showed earlier, we are actually going to rederive certain variables. We are going to rearrange the variables really into a way that makes it more easy to read and interpret the graph that we are going to use to extract the k and the exponent. So firstly, the change of variables. So we are moving away from the areas and the thickness into the KSI space. So these are just a combination of the previous variables. They are not creating anything new, but they are allowing us to just promptly express the k parameters and the 1.25 or whatever exponent that we find for the brains that we have. Okay, so k is going to be the parameter of the force, and we are going to use this k. It is calculated simply by isolating the k variable that we had on our equation before and taking the logarithm of it. And so this is going to be the main variable that we are going to use to calculate what is the actual k for the brains that we're analyzing. The next two parameters, I'm not going to derive them, but I'm going to show them, are going to be expressing, one, purely the purification and the complexity of the brain, and the other one is going to be expressing only the size of the brain. If we have one variable that expresses only the size of the brain, we can just normalize everything to have brains of the same size so that we can better compare rats with whales, for example. And they would have roughly the same size, they would only be different by their complexity and their k parameter. And I'm going to talk how to read a k by s plot. This is really not good. This is really not good. No. So. Yeah. Okay, so this presentation is going to be divided into two sections. The first one is going to be the theoretical section, and the second one is going to be the application of this theory to analyze dolphin brains. Okay, so I'm going to talk about brain morphology, but I'm going to do this using a theoretical physics model and some mathematics to express the variables that I'm interested in. And I'm going to compare different animals under the same... no, this is already bad. Okay, I fucked up. Okay, so I'm going to be talking about the shape of brains, and specifically about dolphin brains. But this presentation is divided into two sections. The first one is the theoretical and context section, and the second one is going to be an application of all of this theory into dolphin brains so that we can study those brains and understand if they are different, why they are different, and how they are different. So I am going to be talking about brain morphology and brain anatomy, but I'm going to do this in a mathematical way. So I'm going to be doing this using a theoretical physics model and a mathematical object that is called a fractal. Well, this fractal object that I'm going to be using to talk about brains is simply a mathematical object that is generated by a recursive rule. So in the case of this star, we have one of its edges that is cut into smaller pieces and create new corners to gain more and more complexity. In the case of brains, what is happening is that we're going to have the surface of the brain, and one of its, in a certain region of the area of the surface is going to be, no, this is fucking awful. Fuck's sakes, man. Lost 10% just about this. Okay, so this presentation is going to be divided into two sections. The first one is a theoretical section, and the second one is the application of this theory to analyze and study dolphin brains. I am going to be talking about the shape and the anatomy of the brains, but I'm going to be talking in a mathematical and physics way. So I want to describe how all of these different shapes are related to one another. And I'm going to be using a mathematical object called a fractal to do so. And a fractal is an object that is generated by a repeating rule. So in the case of this star, what we have is one of its edges being cut into smaller pieces to create new corners. In the case of the brain, what we would see is a patch of the cortical surface being cut into smaller pieces to create the sulci and the gyri that we see. This usually can be expressed as some sort of y being proportional to some sort of rx to the power of r, where r is going to be the exponent that characterizes the fractal that we're talking about. Okay, so what is the fractal that we observe in the brain? It is possible to show that this is going to be the mathematical relationship that characterizes the gaining of the gyrification of the brain. And it is simply a geometrical relationship between variables of the cortical surface. So we see that the total area, which is the area of the sulci and the gyri, times the square root of the average cortical thickness should be equal to a constant k, times the exposed area, which is the area of the gyri only, excluding the sulci, to this exponent of 1.25. And I'm not going to derive the model, but we are going to see the results of this model. If we regress every single terrestrial mammal that we have, they all follow the same regression, meaning that although they have genetically defined a value of total area and cortical thickness, they are all bounded to the same physical model, having the same k value, which is the height of this regression, and the same 1.25 exponent, which is the inclination of this regression. The only seemingly exception are cetaceans, which seem to have a higher height, and the higher height is related to the k. K in itself is not just a number. It is a number that expresses all of the biological properties of the tissue that we're analyzing, which is the gray matter, and the physical properties or the physical boundaries of the system of the gray matter. So the forces that are acting upon the gray matter are the internal axons pulling the gray matter inward, which causes gyrification, but also the external total pressure or the atmospherical pressure in the case of terrestrial mammals, which also causes the brain to crumple even more and gain more gyrification. So for this reason, we believe that, and it was hypothesized that cetaceans would have a higher K value and only a higher K value because they live underwater. And so added to the atmospheric pressure, they would have an added hydrostatic pressure due to the body of water that lies above them. And this is what is predicted. And how are we going to test this? Well, we are going to have to use computational tools to acquire the surfaces and see if this is the case. So, for instance, we have tools such as FreeSurfer that is vastly used for humans and allows us to transform from MRI to a surface, and it can be applied to, like I said, humans, but also other primate species. If FreeSurfer doesn't work, we have also alternative tools, one of which is Stitcher, which allows us to transform not the MRIs, but to transform manual delineations into triangulated meshes and get the same kind of final results that FreeSurfer also generates. So we have the means to acquire the data. Lastly, to finish the first section, I want to be talking about two mathematical enhancements that we are going to need. We are going to need a computational enhancement and a mathematical enhancement. Why we need those? Firstly, we don't have this much data for cetaceans. So get a regression line for one single specimen of cetacean, one single subject, is impossible. So we have to have a way of increasing the data points that we have per subject. And the computational method is going to do this. Secondly, we can just rearrange and shuffle the terms on the equation to actually get the exponents and the k and just plot this promptly and make it more easy to read. Okay, so the computational method that allows us to increase the data that we have works as follows. We get one final surface. From the surface, we transform it back into an image. We lower the resolution of the image, and then we reconstruct the surface again. And we do this over and over again. Why we do this? Because this allows us to reverse the model that gains zerification. Instead of gaining zerification, we are melting the brain, and we are progressively removing the cortical features until we reach its basic shape. So pretty much like with the star that we had initial edges and we gain more corners, we're doing the inverse of this. And this is the procedure that allows us to increase the data points. Because since it is a recursive rule, it is the same rule over and over again, just at different iteration steps. Good. The final mathematical step that we have is to transform the AT, AE, and T into the KSI system. And what is the KSI system? The KSI system is going to express the forces, or rather the actual K that we had before. And this is easily done by isolating the K from the equation and taking the logarithm. And also it is going to express the shape and complexity and the size of the brains. So these are all three things that we are used to and can easily understand. And it is possible to write this mathematically, and I'm not going to derive this for all of the terms, but we write them in this way. And for the rest of the presentation, I'm only going to be talking about the forces and the complexity. And I'm not going to be talking about the size because I'm going to normalize every single specimen that we have so we can more easily compare rats with whales, for example. They will have roughly the same size, they will only differ in terms of their complexity or how far up on the algorithm of gaining zerification are they. So how do we read this? I said that it's going to make our lives easier to read the plots. So basically, if we apply the brain melting algorithm into the K by S plot, what we see is from a higher complexity, so the final brain from the FreeSurfer reconstruction, for example, we melt them until it reaches its basic shape. And only on this K by S plot, we are going to see a constant line, meaning that this constant line represents the 1.25 exponent. And different heights or elevations of this constant line means different k values, and higher k values are going to be higher constant lines. And this is what we okay. Hey, pause, stop. This is better. This is what's good. I'm gonna add a text. Okay, so this is probably better, right? Okay. Then the k by s is darker. Is for the contrast. Okay. Okay, one more. Get in there. Okay, so this presentation is going to be divided into two sections. The first one is a theoretical section, and the second one is going to be an application to the dolphin brains analysis of this same theory. And I am going to be talking about brain morphology and anatomy in general, but I'm going to be doing so in a theoretical physics way, in a mathematical way. So I want to express the gyroid, the sulci, the gyrification, and how different species gain their gyrification in terms of mathematics. To do so, I must first talk about what is a fractal, because a fractal is what universally characterizes all of those brains, as we're going to be seeing later. A fractal object is an object that is generated by a recursive rule. So in the case of this star, we have one of its edges, one of its sizes, sides being cut into smaller pieces to make new corners and gain more and more complexity until we reach a certain limit. In the case of the brain, what we would see is that the cortical surface of the gray matter would fold into smaller and smaller sections, creating the sulci and the gyroid that we observe on the brains. This usually can be expressed in terms of a certain y being proportional to a certain x to a very characteristic exponent that defines what is the fractal that we are analyzing. In the case of the brains, this y and x can be written, and I'm not going to derive this, I'm just going to show you, but they can be written as this. So these are the geometrical features of the brain that make it gain its characteristic gyrification as a fractal object. So we have the total area, AT, which is the area of the sulci and the gyri of the gray matter, times the square root of the average cortical thickness, being equal to the K, which is a constant, times AE, which is the exposed area, the area of the gyri only, excluding the sulci, to the power of 1.25, which is our characteristic exponent, which determines the rate of gaining of gyrification of the cortex in general. This relationship is valid for all terrestrial mammals that we have seen. So, although they have genetically defined the total area and the thickness that they're going to have, they all obey the same physical model, meaning that they all will have a same crimpling or the same gyrification procedure. And this is because they all fall in the same regression line, meaning they all have the same K parameter and the same 1.25 exponent. The only seemingly exception are cetaceans. And to understand why they could be different, we must understand what K actually means. K is a number, for sure, but it is not just a random number. It is a number that encompasses the biological properties of the material that we're studying, in this case the gray matter, but also the physical constraints of the system. So the forces that act upon the gray matter to make it gyrified, to make it fold. And the physical constraints are the axial tensions in the white matter, which pulls the brain inwards, and the atmospheric pressure that pushes the brain from the outside to inside, making it fold even more. This is also valid for cetaceans, but in the case of cetaceans, they have an added hydrostatic pressure, which increases the K value, making them more gyrified than the other terrestrial mammals. Or, well, this is the hypothesis that we're going to test. To test this hypothesis, we are going to need surfaces. And can we acquire them? The answer is yes. We have tools such as FreeSurfer that allows us to transform from MRI into 3D surfaces. And if, for whatever reason, FreeSurfer doesn't work, we also have alternative tools. In this case, we have Stitcher, which is a tool that I developed during my master's that allows us to generalize surface reconstruction for any species as long as we have manual contours that can be transformed into triangulated 3D surfaces. Finally, to finish the first section, I'm going to be talking about two mathematical enhancements that we're going to use for the rest of the presentation. The first one is increasing the amount of data that we need. How do we do this? We're going to apply a computational method that allows us to transform from one data point for one subject into a series of points to one subject, which means that we are going to be able to regress a line for one single subject, and using only this single subject, we can express the K parameter and the exponent simultaneously. The second one is going to be a mathematical transformation, which instead of seeing that regression, that plot that we saw before, we are actually going to see a different plot that allows us to more readily read and interpret the results that we are getting, because we will more readily read the results for k and the exponents that we are trying to get. So the computational algorithm works as follows. We want to transform from the final cortical surface that we have with all of its complexity with SOHCAHTOA and G-Ray into its basic shape, or what was the original form that generated that final fractal object that we see. And we do this by getting one surface, transforming it into an image, lowering the resolution of the image in a very specific way, not an arbitrary way. And from that image with lower resolution, we reconstruct again another surface with a lower quality or less gerification than the original surface. We do this over and over again until we reach the original form. This is a video of this procedure, and we can see that we have one final brain surface for a human being melted down into its original or most basal form. Finally, the mathematical procedure. We are going to transform the AT, AE, and thickness T into the KSI, which are just a mathematical way of shuffling and rearranging the original terms to more readily express the k and the exponent that we want. So k is going to be the actual k, the logarithm of k that we want to get, and we can do this just by shuffling, just by isolating the small k parameter and taking the logarithm. The s parameter is going to be the shape, the complexity, the gerification itself of the brain, and only that. And we're going to have yet another variable that is going to be related to the total size, so that we can normalize different brains, so we can more easily compare, for example, rats or a marmoset with a whale. And I'm not going to derive the other two, but this is the mathematical relationship that allows us to express those features that we are willing to, that we wish to study on the brains. And how do we read the k by n? And for the rest of the presentation, I'm not going to be talking about the I value, because everything that I'm going to be doing is going to be normalized. So all of the brains have roughly the same size, and we don't have to worry about that when extracting the k parameter and the fractal dimension or the exponents. Okay, so the k by s plot. The k by s plot is, how do we read this plot? If we apply the brain melting procedure, we are going to get a series of points for one single brain. So from the right, which is the original brain, to the left, which is the basal form, we should see a constant line on the k by s space. This constant line indicates that the brain has precisely 1.25 fractal dimension, 1.25 exponents. And the height of this line determines how big is the total pressure, or how big is the k value that we are expecting. What happens if we add 1.25 fractal dimension, and different heights of this line express different values of k, meaning different pressures, and higher parallel lines up above will represent higher total pressure. Okay, what if we apply the same algorithm to something that is not 1.25 fractal? What happens? Well, if we have, for example, a cube with a certain thickness, or a sphere with a certain thickness, and these surfaces are totally smooth, they are as smooth as they can possibly be, they have no foldings whatsoever, then we have a defined line with the exponent of 1. That is the most lissencephalic possible limit that a brain can reach, the most smooth surface that a surface can have. And if we have something in between, so if we have a chestnut or a bell pepper, they are also going to be, they can also be melted, and they are going to have different exponents and different inclinations in this k by s plot, meaning that they have different exponents. Oh, fuck, man. Why is this so bad? Okay. So this is terrible. I need to fix this. How am I gonna fix this? How am I going to fix it? I was right on time, at least this. Right? No, I was not right on time. Okay. Applications is not the best. Oh, what can we change? Improvements. Improvements. Okay, so okay, yeah. From here, okay. Triangulated surfaces, just like FreeSurfer. Okay, finally, to finish the first section, I want to talk about two improvements that we can do to our data to better two improvements that we can do to our analysis that allows us to more easily extract the k value and the exponent. Firstly, we need to increase the sample size, and to do this, and this is necessary because for certain rare specimens, such as, well, a lot of dolphins, we only have one single subject. And if we only have one subject, we cannot regress the line and fit the necessary parameters to acquire the... Okay, no, this is already bad. Final triangulated surface, just like FreeSurfer. Okay. To finish the first section, we need to talk about two improvements. One regarding the sample size, and the other one regarding the mathematical analysis that we're going to be doing. About the sample size, for cetaceans, we usually only have one single subject. And to actually be able to calculate the exponent and the k parameter, we are going to have to increase the number of points per subject. To do so, we are going to actually perform a computational algorithm that allows us to flow from the final surface that we have from the cortical surface to its original basic shape that originated that form. And by doing so, we are going to get more data points that are representative of the process that allowed the brain to get its final form. We do this by getting one final surface, moving it back or transforming it back into an image, and then we lower the resolution of this image and we transform it into a new surface with lower resolution. So this procedure, and we do this in a very specific way, it's not an arbitrary way, but this procedure allows us to regress to okay, don't have to talk about this procedure. So I'm going to talk, so we are going to have to perform two improvements to allows us to actually analyze cetacean brains. Firstly, cetaceans usually only have one single subject per species. And if this is per species, and this is a limitation. No. Okay. Triangulated surfaces, just like free surfer. To finish the first section, we need to talk about two improvements that we need in our analysis. The first one is going to be a computational one, and the second one is going to be a mathematical transformation that allows us to more easily read the k value and the exponent value for each of the brains that we have. For cetaceans, what we have is usually one subject per species. So if we want to actually calculate the exponents and the k value, we're gonna need to augment the data that we have. To do so, we are going to use a computational algorithm that allows us to move from the final cortical shape that we have, the final fractal object that we have, that we reached, into its basic form. And we do this by transforming the surface back into an image, lowering the resolution of the image in a very specific way, and then reconstructing the cortical shape again from this lower from this lower quality image, sorry. And we do this over and over again until we reach its basic or original shape that created that final cortical folded brain, that folded surface. This is a video that shows an example of a human brain melting. And as we can see, we progressively lose cortical features until we reach a final blob shape that is mostly lissencephalic, and it is the basic shape of the brain. Okay, this is already very bad. Already really bad. Really bad. Holy fuck. Okay. So, again, at the beginning, yes. Okay, so this presentation, no. This part is pretty good. Okay, so to finish the first section, what we need is to talk about two improvements on our analysis. The first one is a computational improvement, and the second one is a mathematical improvement. The computational improvement is as follows. We need to increase the data sample, the data size, for a single subject. This is because for cetaceans, we usually only have one subject representative for each species. So if we want to calculate the fractal dimension and the exponents are and the k value, we are going to have to increase the data size, the data sample that we have per subject. To do so, we are using this melting brain algorithm, which works as follows. It grabs the final surface, transforms it back into an image, lowers the resolution of this image, and transforms it into a lower resolution surface. And we do this over and over again until we reach its final or its original basic shape that got folded into the final brain that we have. Here's a video that demonstrates this. So we have one very purified and complex brain that gets melted down into its original shape. And each frame of this video actually represents a new data point that we have, a new entry that we have to analyze this single subject. And we can do this for every single subject that we have, or really any mesh that we have. Okay, and what about the mathematical transformation? So instead of working with the biological variables that we have studied before, we are going to re-express this model into more natural variables. So we want to express our model in terms of, one, its force and pressure, which is the K value that we want to analyze. We want to study the complexity and how much you are gaining on this complexity, so the rate of the gaining that we're gaining in the purification with a certain pressure. And also we want to normalize every single brain that we have into one single size so that we don't have different sizes and we can better compare small animals such as a marmoset or a rat with a whale and an elephant. To derive these expressions, and I'm not going to derive these exponents. And I'm not going to derive those. And qualitatively, we can already learn and see where this is going to get us. I'm not going to derive those values, but it is important to see that if we want to express those qualitative informations, we can do this just as a combination of the parameters that we had before. So we are not creating anything new. We are just rearranging and shuffling things around to get what we need. Okay, so we want to get the K value and want to get the exponents. We want to do this by normalizing every single brain, and we are basically going to plot a K by S values of the surfaces that we are melting. And how do we read this? How do we read this plot? Well, if we melt a brain, and from the right to the left we have the most complex brain to the less complex brain, or the basic shape, what we're going to see is, only on the K by S, as we defined before, a constant line means a 1.25 exponent. So any constant line equals 1.25. Different heights of this line means different K values, and higher values and higher lines up above here, they mean higher K values, which mean higher pressures. So this is what we are expecting. But what if we are dealing with something that is not a brain? Well, in this case, we're going to get different inclinations. For example, if we have a cube with a certain thickness or a sphere with a certain thickness, it is perfectly smooth, it has no gyrification whatsoever, so we know that the exponent that we should be expecting is exponents of 1. The relationship should be 1 for 1. And this is the regression line, or this black line is the limit of the lissencephalic limit that we expect to see on this plot. What if it is something in between? Well, we have other objects that have they are not perfectly smooth, they have some degree of folding, and what we see is that even if they have some degree of folding, they are going to have different inclinations with in-between values of 1.25 or 1, with different values that is not 1.25 and certainly not 1. So we can very easily see that if it is a constant line, it is a brain. Different heights, different Ks. And different inclinations means different gyrification process or different folding processes. And this is how we read these plots. Okay, so we have a theoretical model that predicts that dolphins should have a higher K value due to the hydrostatic pressure. We have ways of acquiring the data, and we have the mathematical and computational tools to process this data to test the model. Okay, finally into section 2. Okay, so this is better. Okay, so now we present the whole thing and see the time. Okay, so I'm going to be talking about the shape of brains, And more specifically, I want to describe the dolphin brains and what I found, why are they different, and how are they different. To talk about the shape of brains in general, and I'm going to be talking about a variety of mammals, I need a theoretical model, and I need a physics theoretical model to express this quantitatively. And this mathematical model, or this physical model, is based on a mathematical object that is called a fractal. A fractal is a mathematical object that is generated by a recursive rule. So in the case of this star, we have one of its sides being cut into smaller pieces and forming new corners until we reach a certain limit. The idea is that the brain is doing the same thing. We have a basic shape that folds into itself over and over and over again until it finds a final equilibrium state. This usually can be expressed in terms of a certain y that is meaningful to our system, proportional to a x to a characteristic parameter or characteristic exponent r that defines what is the fractal, the rate of gaining of these features in the fractal object that we are analyzing. It is possible to show that the fractal relationship that occurs in the brain, it can be expressed in terms of these geometrical variables and these specific exponents. So we have the total area, which is the area of the gyri and the sulci of the gray matter, times the square root of the average cortical thickness, should be equal to the parameter k, times the exposed area, which is the area of the gyri only, excluding the sulci, to the exponent of 1.25, which characterizes the rate of gaining of gyrification for brains. And how well does this model fit into the data? Well, if we analyze the hastrial mammals, all of the hastrial mammals that we had, we see that although they genetically define their own total area and their own cortical thickness, they are all related by the same law of gyrification. Since they all follow the same regression line, this means that they all follow the same value of k and the same 1.25 exponent. But cetaceans seems to be different. And why are they different? Well, they are different, the same value of k, which is related to the height of this line, how upwards or downwards it is, and the 1.25 exponent, which is the inclination or the angle of this line. Cetaceans, however, seem to be different, and they seem to be different because they are higher up above, meaning that they have a higher k value. So what is this k value? It's not just a number. The k value is a number that encompasses the biological properties of the gray matter, but also the physical properties of the system. And by physical properties, I mean the forces that are acting on the gray matter to make it fold. So we have, for instance, the axons on the white matter pulling the gray matter inward, which makes it fold, but also the atmospherical pressure, in the case of the hastrial mammals and cetaceans, that pushes the brain inwards and make it crumple and make it fold. However, what differentiates cetaceans, mainly dolphins and whales, from the hastrial mammals is that they live underwater, and due to this fact, they have an added hydrostatic pressure, which makes them have a higher k value. And this is what we are predicting, that the k value of dolphins should be higher. Okay, so can we test this? Do we have the surfaces to extract the thickness and the areas that we need? The answer is yes. We have tools such as Resurfer that allows us to transform from an MRI image into a surface, triangulated surface. We can use this to a variety of brains, but in case Resurfer doesn't work, we also have alternative tools such as Stitcher, which I developed during my master's, that generalized surface reconstructions for different species. and it transforms manual segmentations, not MRIs, into triangulated surfaces. So we seem to have the necessary data to test the model. But before we dive into the section 2, I'm going to be talking about some improvements that are necessary to our case specifically. So in the case of cetaceans, we usually only have one subject per species, which means that we cannot regress a line per species with what we've seen previously. But we need to do this. So we developed a computational tool that allows us to increase the data points per subject so that we can actually regress the line and extract the values of k and exponents. The computational method, which I call the brain melting method, works as follows. You get one final surface, you transform into an image, you lower the resolution of the image into a very specific way, and then you reconstruct a new surface from this lower quality image. And you do this over and over again until you get its basic shape, or the original shape that generated this folded brain. Here's a video that shows this. We have a very gerified brain that melts down into its basic shape, and each frame of this video is transformed into one data point that we collect and we can plot and we can regress to extract the k and the exponents. So this way you can enhance the data, you can just increase the data, that we have per subjects. Also, instead of showing that same regression that we saw before, I'm going to do a bit of the transformation just so we can more easily read the graphs that we're going to read. So instead of working with the total area, the exposed area, and cortical thickness, we are going to be working with Ks and I. This is just a change in the plot. So we want to express the forces or the pressure of the system. This is one parameter, which we're calling K. We want to get one variable to express the whole complexity or gerification, so that we can analyze different gerifications per value of K. And we want to express the size of the brains. The size is basically going to be used to normalize every single brain that we have, so we don't run into issues of scale when comparing rats and marmosets, small mammals, with large mammals, whales and elephants, for example. So I'm not going to derive these expressions. These are not hard to derive, but the main point is that we can see that every single one of these, I'm not adding anything new. I'm just rearranging and shuffling the terms that we saw before, so that we can better express this. And for the rest of the presentation, I'm going to not be talking about I, everything is going to be normalized. So we're going to be talking about K and S. And okay, so how do we read this K by S plot, which is not the plot that we've seen before? In the K by S space, using the brain melting algorithm, what we're going to get is a series of points. So for more complex, or the original shape on the right, to the basic shape on the left, what we see is that this series of points, they should form a constant line on this K by S. And this constant line means that we have a 1.25 exponent, period. So this is very easy to observe on the graph. Also, different heights of this line, if it is higher above, means a higher K value, which means a higher pressure. Good. What happens if we are not analyzing brains, if we find something different? So, for instance, if we have a cube or a sphere or a pyramid, something that is smooth and lissencephalic, and I'm using quotes, what happens? Well, we should have an exponent of 1, but what an exponent of 1 means in the K by S space it means this black line, and I'm going to be plotting this black line throughout the results so that we have a comparison. This is the lissencephalic limit. So once we reach this line, we are no longer losing girification. We are only melting something that is purely smooth, as a sphere would be. And what about other objects? Well, if we melt a chestnut or if we melt a bell pepper, they are not smooth in the sense that they're not lissencephalic, but they are also not a brane. So in this case, these two objects, they have lower than 1.25 but higher than 1 inclinations. They have in-between exponents, so this means that they are going to have an in-between inclination in this plot, and we can very easily identify what is a brane, what is not a brane, and what is the limit of the lissencephalic brane. This is how we read the plots. Okay, so we have a model that we can test, we have the data that we need to test the model, and we have the analysis tools, computational and mathematical tools, to analyze everything. Finally, we reach section 2. So we are going to answer 2 questions. First one is, are dolphins' case actually higher as we predicted before? Is it actually dependent on the total pressure? So is the model actually valid or not? And secondly, this is a series of complex weird steps, and this is a series of complex steps, and so we must know how much can we trust this process. So how robust are the results that we're getting? So let's answer the first question first. Okay, so I must talk about the Brazilian Neurobiodiversity Network, which is a network of different institutes in different states in Brazil that collects, extracts, preserves, and analyzes brains of different animals in South America, specifically in Brazil. And it is because of this network that I was able to acquire the images and the surfaces for 2 dolphin brains that I'm going to be analyzing as in the next section, in the next 2 slides. Also, because of this network, I was able to acquire via an international collaboration, the brain of a Steller sea lion, and via several resources that I could find online, I'm going to also be analyzing a series of primates, including humans, so that we can compare dolphins with other terrestrial mammals. Okay, so first things first, one species that we tend to understand the most, the humans. So if we melt our brains, what do we look like on the regression, on the K/S plot? Well, we see that by melting human brains, we get roughly a constant line, which means that the exponent is 1.25 for humans. And we have this band, this blue band of possible values of K that express a possible variation that we could have for humans. And also, we can see that using the 2 different reconstruction methods for the same subject, we don't see a significant variation or a systematic shift or anything like this. In fact, we can say that regardless of the reconstruction method that we are using, we get compatible results. So reconstruction method should not be an issue when we are analyzing brains using the brain melting procedure. Okay, so if this is our baseline, how other animals compare to humans? Well, let's analyze the other terrestrial mammals and a semi-aquatic mammal, the Steller sea lion. And what we see is that all of these terrestrial or semi-aquatic mammals, they all follow the same trend of humans. In fact, they are compatible, even in the case of the Steller sea lion, with the same K value. And they all have also the same 1.25 exponent, because they are all constant in the K/S space. Well, finally, we can analyze the 2 cetaceans that we have. And what do we see? yes, they do have a higher than expected k-value. So even considering the whole 2 sigma variation of the humans, we see that cetaceans are in fact above the expected variation for terrestrial mammals, meaning that they indeed have a higher k-value. However, what we see is that not only they have a higher k-value, but they have a higher and increasing k-value, meaning that the inclination of this of the series of points for cetaceans, it is not constant. And if it is not constant, it means that it has a higher than 1.25 exponent. We estimated that the exponent is between 1.28 and 1.3. And what does this mean is that we are probably seeing a new gerification mechanism that occurs only in cetaceans. So whatever is going on, whether it's physical or biological, and we are still trying to understand what is going on, the cetacean group seem to have their own gerification law. Either they have an added term that causes more gerification, they have an extra force, they have something extra that makes them be more gerified than the average terrestrial mammal or the general terrestrial mammal, or we neglect a term in our model that is present in terrestrial mammals, but for whatever reason it is present but not that relevant. And we don't know what this term is, we are still trying to figure out, but this basically means that we have new physics or new biology going on in cetaceans, and this is something that I'm going to be studying and investigating in the future, what might be the causes of it. We are concerned that this observation is actually caused by a methodological error. So we need to trust the method that we have. And how do we do this? Well, we are going to be inserting bad quality data into the model and see what happens. And by bad quality data, I mean bad image acquisition or bad segmentations, or a manipulation of resurfer that generates surfaces with varying cortical thicknesses, so fake surfaces. But these are controlled and understandable errors, and by seeing what happens, we can then maybe infer if that was the case or not with cetaceans. So by using bad images, what we see is a trend in the that lowers the expected k-value but preserves the 1.25 exponent. And we can see this by comparing the blue points, which are the good images that we use to make the average human trajectory, with images that belong to the same repository, with the same image resolution, same 7000, same acquisition protocols, but they had bad image artifacts, several bad segmentations or stuff like this. And the trend is to lower the k-value and not increase the k-value. This is precisely the opposite of what we observed in cetaceans. So whatever is happening with cetaceans, we can assume that is not due to bad or poor image quality. Okay, but what about the surface reconstruction? Well, with surface reconstructions, what we see is even more drastic, because by varying surface thicknesses, what we see is that the thinner it is, the brain, the lower the exponent is, and the lower the k is. So this is twice the opposite of what we see with cetaceans. Cetaceans have a higher k and a higher exponent, higher than 1.25. So also we are discarding the possibility that what we observe with cetaceans is due to bad reconstruction. And with that, I would like to just give you two takeaways. the first one, the most significant one, is that dolphins do seem to have their own eutrophication law, and whatever is causing it, whether it's biological, physical, we still don't know, and we are going to investigate this. But this is a new science, and this is exciting stuff. And the second one is that using the KSI parameters and the brain melting algorithm, we can just analyze very interesting features of the anatomy of brains in general, and we can quantify them as well. So this is the team that is involved with this research. There's myself, my two supervisors, Bruno and Camilo, and the two anatomists that helped a lot with the segmentations, Nina and Luana. And that's it. Okay, we have it. We have it. Okay. Break. Great. Okay, I'm gonna go eat a sandwich and be right back. Okay, and we are back. Oh boy. Also washing my clothes, so there might be noise on the house. And there's noise outside. Hold on. And we're back again. Again. It is back again. Okay. Okay. Just check YouTube if everything. The sound's kind of low, right? Test sound, test. Oh yeah. Why is the sound low? Did I change something? Okay, 6.7. Okay. How's that? And now I'm gonna be testing with cell phone. Still low, man. Still low. This is weird. It shouldn't be that low, right? Oh no. This is good. This is good. Yeah. This is good. Alright. So now with the timer on my phone, not on the web, because this is the clock that I'm gonna be looking at during the presentation. Okay, no more Portuguese until tomorrow to get used to speaking fancy words in English. And we shall begin. Okay, so I'm gonna be talking about shape of the brain in general. More specifically, I want to talk about the shape of dolphin brains. And this presentation is going to be divided into two sections. The first one is going to be the theoretical section and the context section, and the second one is going to be the application of this theory into dolphin brains and how we're going to identify if they are shaped differently or not. Okay, so this presentation is about anatomy and morphology, but it is not as a biologist would study. In fact, it is as a physicist would study. And I'm going to be using a theoretical physics model that is based on a mathematical object called a fractal to analyze and quantify all of these different brains with one single equation. But first, fractals. What are fractals? Well, fractals are mathematical objects that are generated via a recursive rule. So in this case, we have a star that has one of its sides cut into smaller pieces to create new corners, and we do this over and over again until we find a certain limit. In the case of brains, what we're gonna have is that the gray matter folds into itself over and over again to create the sulci that we see and observe in different brains. This object can be in general expressed in terms of a certain y to being proportional to a certain x to the power r. And r is usually the fractal exponent that characterizes the rate of gain of these structures that we observe on the fractal. So what is the mathematical relationship and what it involves in the case of brains? In the case of brains, what we have is that we have a geometrical relationship between certain cortical features, and they are, and I'm not going to derive this equation, but they are, as we've seen before, a power law, so they are describing a fractal relationship of the brain. So we have the total area, AT, which is the area of gray matter, which includes the gyri and the sulci, times the square root of the average cortical thickness, and this should be equal to a constant k, times the exposed area, which is the area of the gyri only, to the exponent of 1.25. And this law of gyrification, if we analyze a variety of brains, we see that all of them seem to follow the same rule, the same law. They fall in the same regression line, meaning that although genetically each species is going to have a predefined value of total area and cortical thickness, they are all following the same fractal law, the same physical model that establishes how much is going to fold according to this law, and they all have the same k value, which is the elevation or the height of this line, and the same 1.25 exponent, meaning that they have all the same inclination of this regression line. The only exception, it seems to be the cetaceans, so the dolphins and the whales. And the reason for this is related to the k parameter, so the height of this regression. And the k value, the k parameter, is not just a number, but it is a number, but it is a number that encompasses the biological parameters and also the physical parameters of the system. And the physical parameters, I mean the forces that act on the system. So we have in the white matter, we have the axons that pull the gray matter inside to create the folds, but also we have the atmospheric pressure that acts upon the surface, pushing it inward and making it fold even more. In the case of cetaceans, not only the atmospheric pressure is exerted, but also the hydrostatic pressure, because cetaceans live underwater. And this means that cetaceans should be shifted upwards in that regression, meaning that they are more gyrified than expected for other animals because of this effect. Can we test this? This is a hypothesis, so can we test this? Well, to do this, we need, first of all, surfaces. And fortunately, we do have the tools to do that. We have, for example, FreeSurfer that allows us to transform from MRI to triangulated meshes. And if FreeSurfer doesn't work, we also have alternative tools such as Stitcher that allows us to transform from manual delineations also into triangulated surfaces that are or should be equivalent to the FreeSurfer surfaces that we get. Okay, so just one more step before we can actually go into testing this hypothesis. For cetaceans, it is very uncommon that we're going to have a large sample size. In fact, for the vast majority of species, we are only going to have one subject, and sometimes none. But if we have one subject, we cannot make a regression to fit two parameters. We only have one data point. So we have to increase the amount of data that we have per subject. To do so, we have a computational method that allows us to multiply indefinitely the amount of data points that we get. This computational method works as follows. We get one final surface, we transform it into an image, and we lower the resolution of this image in a very specific way. And then we reconstruct again a new surface from the lower quality image into a new surface with lower resolution, with less details. And we do this over and over again until we reach the basic form of the brain. So remember the start that we saw before? Well, we can kind of do the same with the brains. So if we have a brain that has a final defined shape, we can melt the brain, so we can use this melting brain algorithm to achieve the initial basic shape that originated all of the surface folding and the sulci and the gyri that we see in the final shape. So each frame of this video is actually going to be a new data point, new data entry that you can then use to make a regression and extract per subject the value of its k and the value of its exponent. Last improvement is going to be a mathematical one. So I know that I talked about the total area, exposed area, and cortical thickness, which we can all understand and comprehend what they are. But these are not the most natural set of parameters, set of variables that we can use to study this model. So I present the k, s, and I. The k, s, and I are going to be variables that are going to be expressing the following properties. So k is going to be expressing only the forces and the pressures. So this is what we want to measure. S is going to be expressing the shape or the complexity, which is going to be used to determine that exponents or the rate of the gain of the gyrification. And the final one is going to be the size parameter, which are going to use, and it's going to vanish for the rest of the presentation because I'm going to use it to normalize the size of different brains so we can more easily and in a single plot compare rats and marmosets with whales and elephants, for example. Just for the math enthusiasts, this is how you define those variables. But what is important to see is that all of these variables, and I'm not deriving them, but all of these variables are just a fancy combination of what we had previously. So I'm not adding anything new. I'm just rearranging the terms so that we can more easily analyze the plots that we have. Okay, so like I said, no I, because everything's normalized. We're gonna have a k by s plot. The k by s plot, when we perform the brain melting algorithm for one single subject, what should we see? What should we expect? From right to the left, we have the most complex shape being melted down into its basic form. And if this trajectory, this sequence of points, is a constant line, this basically means that we have exactly 1.25 exponents. So any constant line in this plot have 1.25, so this is very easy to observe visually. Higher values of k mean that we're gonna have a constant line. However, it's going to lie up above on this k by s plot. So we're gonna have to have a comparison between terrestrial and aquatic mammals or cetaceans. Okay, what about other shapes? Something that is a lot more easily understandable. So a sphere or a cube or a pyramid with a certain thickness on its sides. What does it look like? We can plot the equivalent of exponents of 1.0 to those basic shapes that we know, how they scale. They are basically invariant, they do not fold in itself, and we have this black line that represents the lissencephalic limit of each melted brain. And what about other structures? So if we have a chestnut or a bell pepper, for example, well, they are not perfect lissencephalic, so they have some degree of folding. However, they should not follow the same fractal properties of the brain. And this is what we see. They have a different inclination, so they are not a constant line. They have therefore a different exponent, and somehow they will reach eventually through the brain melting algorithm. They will also reach the lissencephalic limits, so they will become well, quite smooth in a sense. Okay, so this is how we read the data. So far we had the theoretical model, the data that we can use to test the model, and the way that we're going to analyze this data so that we can actually test for the hypothesis of the hydrostatic pressure being different in dolphins. So for the second section, we are going to answer the two main questions. are dolphins' case actually higher as predicted? And secondly, all of these steps are very complex, so how robust and how much can we trust those results? Okay, so for the first question, I must talk about the Neurobiodiversity Network, which is a network of different institutes in different states in Brazil, which allowed me to collect, which they normally collect, extract, preserve, and analyze brains, but they also provided me 2 brains and 2 MRI images that allow me to get 2 surface reconstructions for 2 cetacean species, 2 dolphin species in Brazil. Also, due to the network, we have an international collaboration which allowed me to get the brain of a sterile sea lion, and through online resources I was able to acquire data for a variety of different mammals, including mostly primates and a lot of humans, really. Okay, talking about humans, so I'm going to use humans as a baseline, and I'm going to go step by step on each one of the animals that we're going to analyze. So for Homo sapiens, us, what we see is that when we melt each of the brains, we get one average trajectory, which is shown in blue, and we get a certain range, a certain span of variability on the K value. But in general, we are a constant line, meaning that we have a 1.25 exponent. And also, I added 2 reconstructions for the same subject, same MRI, however, using the 2 different methods. And what we see is that they are also compatible. So regardless of the method, and for all humans that we have, we are going to have a certain variability of K, but it doesn't matter what reconstruction method that we use. We are going to have a constant K, meaning 1.25 exponents that we see throughout the human melting process. For other terrestrial or semi-aquatic mammals, what do we see? Well, if we melt those, what we get is that we're going to have compatible K values and also constant K values. So the terrestrial and semi-aquatic mammals, they all follow the same 1.25 exponents as predicted previously, which is expected for sure, but it is also nice to see that the sterile sea lion, which it does dive a little bit but spends most of the time on land, also have the same K value. So it shouldn't and it doesn't have a different K value in this case. And finally, for the cetaceans, so what we are expecting is a higher K value, so they should be outside and above the human range that we established as a baseline. And here we have it. So our prediction seems to be correct. All of the cetaceans do have a higher than expected K value. However, they have a higher than expected but increasing K value. And this basically means that instead of having a 1.25 exponent, they have a higher than 1.25 exponent. We estimated that this exponent is going to be between 1.28 and 1.3. And how do we interpret this? We are still not sure. But what we think is happening here is that each the cetacean family, the cetacean group, they have an added cortical feature. They have an added cortical gyrfication mechanism that allows them to gain more gyrfication than other terrestrial mammals. And this effect might be present in terrestrial mammals but be so negligible that we don't observe it, or it might be an entirely new feature that is exclusive to cetaceans and that we still don't know what it is and what is causing it. We don't know if it's biological or physical. And we are investigating what could be the causes, how could we adjust the model to fix for this variation, or if they actually have to have a model of their own to explain why they have such a unique behavior when compared to all of the terrestrial mammals that we have. Okay, So can we trust this? I mean, is that a fair conclusion to be drawn from the results that we're getting so far? So how we're going to test this? Basically, we're going to introduce systematic errors into the brain melting, and we're going to see what happens and see if they match or they do not match the cetaceans results that we get. So if we use bad quality images or bad quality segmentations on those images, what kind of results do we get from the surface from FreeSurfer, and how these interfere with the melting algorithm? Additionally, if we just get good images, but instead we trick FreeSurfer into creating bad surfaces. So we manipulate the cortical thickness, for example, and we get partial thicknesses, and we plot those results from the brain melting. What do we get? So for the bad images, what we see is that there is a clear tendency of lowering the k-value, which is represented by the red points, with respect to the average or the average human trajectory of good images and good segmentations that we see, and we had seen before this, that was used to calculate the average human trajectory. And since we are lowering the k-value for bad images or bad segmentations, what we can conclude is that this is the opposite of what is happening with cetaceans. So whatever is going on, if it is a methodological error in the case of cetaceans, it is not due to a bad image or a bad segmentation. Okay, so what about bad surface reconstructions? How does this effect interfere with the results? If we plot those melting brains with varying cortical thickness, what we see is that not only we lower the expected k-value the thinner the brain gets, but also we lower the fractal dimension, we lower the exponents of 1.25. And this is twice the opposite of what's happening with cetaceans. So basically what we see is that if there was a methodological error in our analysis, it is not due to bad segmentation or due to bad surface reconstruction. And with that, it is fairly reasonable to assume that, in fact, cetaceans do have their own way of purification. So, and this is part of the two takeaways that I like to have from this talk. First, dolphins and cetaceans in general seem to have their own purification law, and we don't know what is causing it, but it is probably unique to them. And the KSI plus brain melting algorithm allows us to extract some very meaningful and interesting information from the anatomy of the brains that we have, and it is possibly a versatile tool to investigate anatomy in general. The team that was involved in this research was, well, myself, my two supervisors, Bruno and Camila, and also the two biologists, Nina and Luana, that helped a lot with the segmentation specially. And that's it. Okay, so we have it. And it's 22 minutes. 21 minutes. Okay. Okay. We finally have it. Yes. Oh. Okay. Dustin. How long has this made? This 5. Okay, 4 hours of training. Okay, that's a lot. That is a lot. Oh. Okay. Uh, Now it's best to stop, have one presentation for morning for the thing with the other thing. Sorry. Thing. Wednesday. Okay. Okay, so now we have it. Okay. um, eh, for sure not. Nothing of 11. Have one. Uh, uh, oh, yeah, that's yeah. One. Not work. Well, well, anyway. Anyway, that's it. Like tomorrow, this. We're ending the live stream. That was 4 hours of training for the presentation tomorrow. And that's pretty much it. So, look. In case it doesn't work, I'm just going to send them the link for this last part of the presentation, which was pretty good. Okay, anyway, that's it for hours. See ya. Bye.